So welcome to the last homework assignment of the of the semester. As you are surely aware, the basic schedule is we're going to do this homework today and possibly into Thursday, probably into Thursday. Next week we are technically off. That is the time you guys should do everything you can to catch up, to finish up assignments that you never quite finished or didn't fully understand. I was planning on being out of town, but I was also hoping to have been vaccinated fully by this point. I will not be fully vaccinated until tomorrow, so I'm not traveling. So I will be around next week to answer questions, even though we have scheduled a class to be off. I believe these links will work. So if you guys wanted to establish a study section or a review or whatever, talk amongst yourself. I think these links should work. Should there be any desire for you guys to do such a thing, I will neither encourage it nor discourage it. That is totally up to you. The week after next, on Tuesday, we're going to do a reading. I should probably go ahead and post that. One of the readings will be a very long summary of everything that was known about quantitative genetics, mostly in experimental systems, as of like 1990. And we will find that shockingly, we don't know a whole lot more than we knew then. But it is a historical review of the entire field that is worth reading. And I think there will be another paper on the relationship between genetic variation and recombination. I think that's the one I decided to assign. After we do those readings on Tuesday, we will have an exam on Thursday. And the exam on Thursday will be exactly like the midterm. You will email me a sheet of paper that has your study notes, and I will send you back an exam. And sooner or later, you will send me your completed exam with the promise you haven't cheated on it. And it will go just like it did in the midterm, probably. That you guys, I'm sure, will do well. I'm sure there'll be a few questions that fool most of you. And I'm sure there will be a lot of questions that a lot of you do very well on, because you're doing an amazing job in this class so far. I'm really I hope everyone is proud of how they're doing. Before we get to today's homework, are there any questions about class structure, about procedure, about any of that kind of stuff? Homework 10 was long. It was hard. It was painful. But hopefully, by the end of today or the end of Thursday, last week we derived every important result in quantitative genetics, really, honestly. All the really important ones we've now derived. And as of today, we should be able to apply everything that we derived last time to very sort of useful applications involving, sort of animal husbandry, to useful applications involving, how you would conduct a modern disease study. So we start out with problem 1 with Linnea. I know you just signed in. Sorry if you're still working life together.
I think that tends to happen to me, I think.
Sorry, I'm sure I haven't given you permission. Let me give you permission. There we go. All right.
All righty. Okay. Okay, can you see that? All right, so problem 6.1, what's heritability of a trait when VA is 2 and VA is 3? Correlation between parent and offspring. So for this problem, I just substitute into the expression for heritability. And then between, what was it, parent and offspring, I think it was just R times H squared. So R for parent and offspring is 1/2. And that's how I got that correlation value.
What did did I write the question down wrong, or did you write the question down wrong? I must have
No.
written the question down. Huh.
Did I do the wrong?
Pasted it. You've cut and pasted it, and I retyped it. So I'm guessing you wrote the question down correctly. When I wrote it down, VA was 3 and VE was 2.
Okay. Well,
So,
it might be the copy of the text I have
yeah.
too.
So since you cut and pasted it, I'm guessing that that you have the correct numbers, and I have and I'm dyslexic. Okay, but yes, with VA of 2 and VE of 3, heritability is 2/5, and the correlation of parent and offspring looks like R times H squared. So R between parent and offspring is 1/2. H squared is 2/5. So the correlation between parent and offspring is 1/2 heritability, or in this case 1/5. Or if you use my numbers, 3/5 and 3/10. I don't know why I did. God, that's a weird thing. Are there any questions about this? So in a few seconds, hopefully, we'll talk about why we call VA over VP heritability. We will talk about why we call something a regression. We'll do all of that. But at this moment, all we need to know is the definition of the word heritability is VA over VP. And heritability is related to the correlation between relatives. In general, the correlation between relatives is R R times heritability, unless there's some VD running around. Questions here? This is all sort of very clean, very nice. You probably even learned a formula like this as an undergrad at some point or another. Up next with problem 2 is Mega.
So I totally did not read the part in the question where it says the whole table, and I just did the first one.
Well, that's fine.
But
So what do you got
basically,
here?
I used the H squared equals VA over VP formula, and they gave us VA over VP. And then I multiplied by R, which was 1/2 for the first one, and I got 1/3.
That
But I
sounds
didn't.
that sounds excellent. That sounds like the perfect start to this problem. Here, I'll share my my full screen so you guys can see all of it. Yeah, this problem went on to this homework went on for a while, and can you guys see my my PowerPoint here? So I have, if I've copied the numbers correctly this time, but I got at least the same copy as Megan did, so that's a good guess. VA is 2, VP is 3. All the other I wrote down all the other components are 0, and let's go through the whole sort of table. Parent to offspring have a 0% chance of sharing 0 alleles, 100% chance of sharing 1 allele, 0% chance of sharing 2. Full sibs have 25% chance of sharing 0, 50% chance of sharing 1, 25 of sharing 2. Half sibs have a 50% chance of sharing nothing and a 50% chance of sharing 1. First cousins have a 75% chance of sharing nothing, a 25% chance of sharing 1. R, which is equal to R2 plus 1/2 R1, is 0.5, 0.5, 0.25, and 0.125. R, the coefficient of relatedness, is the fraction of the genome shared between the individuals. Parent and offspring share 1/2, full sibs share 1/2, half sibs share 1/4, first cousins share 1/8. Hence Haldane's joke, would you give up your life for your brother? No, but I would for 8 cousins. So R is an 8. I'm sorry, was there a comment there? So the correlation when VD is 0 between any pair of relatives is R times heritability, or RVA over VP. So the problem says VP is a third. We've worked out R in this table. The problem says VA is 2. So go ahead, do the math. And if I'm not an idiot, you would have, I got 1/3, 1/3, 1/6, and 1/12, which looks about right. Does anybody have any other questions about this? This is what you're really supposed to get out of this, is the correlation between relatives is R times heritability. Unless there's unless there's dominance going on, at which point it would be RVA plus R2VD. But as you can see, for everything other than full sibs, R2 is 0, which is why, unless you're talking about siblings, full sibs, or some complicated pedigree relationship, we tend to, in our head, just simplify this to RVA over VP, R heritability. Because rarely, for what you're looking at, will there be any significant probability of sharing 2 alleles in common. Is this clear to everyone? Okay.
Can I
Yep.
ask kind of a silly question? Just
Not silly.
It's like,
There are no
I wanna
silly
catch-
questions here. This is really
I just want to
important.
catch an error that I made, I think between question carrying over question 1 to 2. So VA plus VE is VP.
Yes, I would say
Okay.
VP is the sum of all imaginable components.
Right. So genetic plus environmental.
Yep.
Okay, cool. I made a very silly mistake.
That's okay. That's good. That's good. This is the time to make the silly mistakes. So when the exam comes, we don't lose 1 or 2 points for the silliness. Other questions here. Before we go on to problem 3, because there is a term of art in problem 3 that may have gone by very, very fast, and a set of assertions in the book, in both Gillespie's book and I think in Falconer, that don't fully capture what's going on. I probably should have had you do a whole bunch of things on the mid-parent. Because I didn't have you do things about the mid-parent, I'm going to do them for you. So the first thing we need to know is, what does that term of art mid-parent even mean? And what it means is it's dad's phenotype, which I'm going to write as PP for the phenotype of pop, and PF for the phenotype of a female. I've mixed and matched these things so badly. That's because I'm using M for mid-parent rather than mother or mom or maternal or paternal. So we have a PP for paternal phenotype, a PF for maternal phenotype, even though, and a PM for mid-parent. And the mid-parent is defined as nothing more than dad's phenotype plus mom's phenotype over 2. It is literally 1/2 of dad plus mom over 2. So we're going to first, before we start talking about the correlations between, this is now a random variable. It's not a person, it's not a thing, it's a random variable that was created by adding together the father's phenotype and the mother's phenotype, which we think in this context as random variables, and dividing by 2. And we should talk about some of the moments in correlations of that random variable, which is like an abstraction. So what is the expectation of that random variable, PM? Well, it's the expectation of PP plus PP. That should be a PF. I will make this mistake more than once. This is supposed to be mom's phenotype. It should be dad's phenotype plus mom's phenotype over 2. God damn. Which is 1/2 of the expectation of dad's phenotype plus 1/2 of the expectation that should be mom's phenotype, which is 1/2 of, I just did it all the way through this. I'm an idiot. which should be 1/2 0 plus 0 is just 0. So the mid-parent has expectation 0. The variance of the mid-parent is first, recall when you pull a 2 out of it, when you pull a constant out of a variance, it comes out as a square. So it's 1/4 the variance of dad plus mom plus twice the covariance between them. I can't believe I made those VPs anyway, which is of course the variance in dad plus the variance in mom plus twice the covariance between dad and mom, which we're going to assume is 0 because we're going to assume dad and mom are unrelated. Hence, the variance of the mid-parent is half the population variance. The covariance between mid-parent and offspring, oh, now I'm getting it right and calling it PF. The covariance between the mid-parent and the offspring is, again, just dad's phenotype plus mom's phenotype over 2, covariance with the offspring, which again, as we know, I can now write this as the covariance of this thing with that, the covariance of this thing with that, which I rewrite as the covariance of dad over 2 with offspring and the covariance of mom over 2 with offspring, which I can then pull out a half here, I can pull out a half there, and I get a half the covariance of dad with offspring and half the covariance of mom with offspring, which the covariance between any two relatives is RVA plus R2VD. So this is RVA plus R2VD. This is RVA plus R2VD. Between parent and offspring, R2 is 0, R is a half. That term is VA over 2. That term is VA over 2. So I get VA over 2 plus VA over 2 times a half, or just a half VA. That's for the covariance between this abstraction, mid-parent and offspring. And now I'm going to get the correlation between mid-parent and offspring, where if you'd looked up a table, you would have seen there was a mysterious square root of 2 in a table somewhere. If you'd ever wondered where that came from, the correlation between mid-parent and offspring is, of course, the covariance between mid-parent and offspring divided by the variance in mid-parent times the variance in offspring. The covariance between mid-parent and offspring we just established up here is VA over 2. The variance in mid-parent is VP over 2. The variance in the offspring is VP. Hence, the correlation between mid-parent and offspring is VA over VP with a square root of 2 in there. Lovely. The regression coefficient, on the other hand, between offspring, the expected value of the offspring given the mid-parental value, the expectation of offspring given mid-parental value, is covariance of PM with what the hell did I write? It's the covariance between, this should be offspring and mid-parent, divided by the variance in the mid-parent. That covariance is VA over 2, that variance is VP over 2. Hence, the regression coefficient of mid-parent on offspring is H squared. And that is where history started. So Galton in the 1870s spent a lot of time taking values, like measuring parents and measuring offspring. And what he would do is he take dad's measurement, takes mom's measurement, average them together, which we now call a mid-parent, and then plot the offspring's value as a function of the mid-parental value. And he showed that the slope of the line that predicted offspring given mid-parental value was always less than 1. So what Galton observed was that if you take a male and female and then you sort of average them together, that average tends to be closer to the mean than say the more exceptional of the two parents. And then if you look at the expected value of the offspring, given the average of the two parents, the offspring are closer to the population mean, heritability is less than 1, than the average of the two parents. This caused Galton to believe that the way heritability worked is heritability took whatever variation was in this generation and pushed it back towards the mean. It's a very strange view, but it's why he called it regression. And he thought of it as a bad thing. Galton thought, I'm brilliant, but my wife's maybe not quite as bright as me, but together we're still pretty smart. But our kids are going to be even dumber than the average of us. Our kids are going to regress towards the mean. And society as a whole is regressing towards the mean so that society is becoming dumber and less brilliant like I am over time. This was why we call it regression. And this was the observations that gave rise to the belief that regression happened. And regression was the dominant viewpoint. Like everyone, for the most part, believed this is how inheritance worked from about 1870 till, well, really Fisher in 1918, until we proved why all these things work the way they do. So this was a serious problem for say, Darwin. If Darwin struggled with, he correctly intuited how natural selection worked, but he didn't understand, like, if you believe this is how inheritance works, it creates all sorts of problems for Darwinian evolution. And this viewpoint that this is how inheritance worked probably slowed, sort of the acceptance of both Darwinian ideas, and it certainly gave rise to some very, very kind of peculiar and nasty ideas of what society should do to make itself better. It was this kind of viewpoint that gave rise to a lot of things we now call eugenics. But that's sort of a topic for another time. But so the regression of mid-parent on offspring has slope heritability, and that slope is less than 1, because you all understand it was created by a large number of Mendelian factors, and VA is necessarily less than or equal to VP, so the slope is less than 1. But despite that, there is no change in variance when we go from one generation to another. We are explicitly assume, in fact, VP remains the same. Do we have any questions about this little peculiar thing called a mid-parent?
So, yeah, actually, if the assumption is that using the mid-parent kind of gets you a better approximation of, what each parent is contributing, is that affected by, I don't know what the right terms are, but the spread between the parents in terms of, it's more likely they're going to be similar with the spreading, right? So that might have an effect on it versus if you had very different parents.
I think the real reason to think of the mid-parent is because it's a very, very practical quantity. If I'm doing a breeding experiment. So if I have some organism that I can hardly tell the difference between boys and girls, I certainly don't want to sit there and measure boys and girls separately, but I just want to sort of say, make a cutoff and have everybody be beyond that cutoff. I can then tell you what the mid-parent values are because I know everyone's beyond that cutoff. And it's a very, very practical creature. I don't think it has much intuition to it, other than when I do these sort of truncation selection experiments, I know what the mid-parent is real quick.
And I guess what I'm saying then is you lose some information though, right? About
Oh, absolutely.
what maybe the different pairings would give you.
You bet.
Totally.
Totally. Yes. Yeah. And if there was random mating, I might not have lost a lot of information. But if there's a sortative mating, I've lost so much information, I might come to the wrong answer. Some kinds of assortative matings could do all sorts of perverse things to me that I'm assuming away by assuming a random mating. Other questions on this? Let's see. So Michelle is still not back. Carmen, you're up with the rest of problem 3. Now that we have a definition of what mid-parent is.
Sounds good. Okay, so I actually realized I made some typos on this. So right here, I wrote, I'm sorry?
Me too.
Oh, yeah. I accidentally wrote the regression when it's actually the correlation. So I used the equation for the correlation of the mid-parent, and I got the heritability, and then calculated the VP for the mid-parent and used that to I'm not sure. Oh yeah, I used that to I'm not quite sure what I did actually.
Yeah, so it looks a little funky. Let me share my screen at the end of, let me go back. But yeah, so once we get, I can share my screen. I really can. I know it. No. Do you see the PDF or not? You guys are seeing the PDF? Yeah. So once we have all those definitions in place, the problem says the correlation is 0.76. So heritability is 0.76 times the square root of 2, or about 2/3. If the two parental heights are 3 and 1, that means the mid-parent value is 2. So the expected value of the offspring, given the parental value was, what did I write, 3? Supposed to be 2. I just calculated as 2 and then wrote a 3 here. Good Lord. I'm tired too, guys, obviously. So the expected value of the offspring should be the regression coefficient times the mid-parent value, which should be the number 2, not 3. So it should be heritability times the number 2, which is 2, which is like 4/3, rather than the number 2. So I think your value you may have shown of something like 4/3 is correct, despite my not being able to copy correctly. All right, from 2 lines over. Sorry. So this should be the number 2. That should be the number 2. That should be the number 2. That should be the number, 2/3 or so, 1.4, something like that. Questions? Sorry. Yep. Brooke, sorry.
Yeah, no, I think it's mostly just confirming. So because it's 3 plus negative 1, right?
It said -1?
Well, I'm wondering because the way that the question is worded is it says that one of the parents is 1 inch below the mean, and then
What's that below the mean? Oh, if it is below the mean, that should be -1. In which case, if that said -1, boy almighty, I got to wake up while doing this homework. If it said -1, the mid-parent is 3 minus 1 over 2, which is the number 1. And in which case we have now the parental, which we now have the regression, is still 0.67 times the number 1, which would just give you 0.67. If the problem read 1 inch below the mean, that would imply that should be -1. And I'm not reading carefully enough. I'm sorry. I'm glad some of you are paying more attention than I am. All right. Up next let's see, is Jim with whatever the next problem is.
We're on 4, right?
Yep, 4, I think.
All right. It's like a little cheating, but gave us a whole bunch of numbers. Let me make sure I have the right question. Gave us a bunch of measurements for weights from a single parent and offspring, which are, I think, deviations from the mean, and asked what the heritability is. So these are all those numbers, and I just kind of put them in R to do the correlation quickly. And so from parents, you get all these numbers. From offspring, you get all these numbers. And you just generate the correlation of them, which ended up being about 0.43. And we know that correlation for parent and offspring equals h squared over 2. So I think that got messed up, but you just use that equation to calculate out what heritability is, which is about 8.87.
That's exactly right. I also wrote down the expected values, the variances that you'd need to have calculated the covariance from, but we got the exact same answer. Does anyone want to look at this? You can, because we live in an era when we don't have to do these things on our fingers anymore, you can very much use Excel or R or any of your favorite tools to calculate that correlation, or you could have done it by hand and gotten this exact same value. Did anyone do this by hand and struggle and not get 0.87 and want to talk about it? Otherwise we're going to move along.
Actually,
yeah.
I didn't get this answer, but I think I also was just being a little bit, maybe I was being a little lazy with this, but I'm wondering if my approach was
You want
where
to
you
show
could.
it?
Yeah, sure. I'll show it. It's not great, but I'll show it. Basically what I thought about doing it in my brain last night was thinking that I could, kind of work through it by approaching it with the slope. And I think I only did 2 points. So, I could have plugged this into R and actually made the slope of the line, solve for the slope of the line, and then use that in the equation. But yeah. I think I just was trying to finish. So,
so you took a couple of these points, estimated the line from like 1 or 2 of them, and from there back calculated what heritability was, and got sort of in the right ballpark. Yeah, okay, whatever. That's the.
But I think if I were to do it differently, I would probably have put it into like an actual program and really calculated the slope with the line. But that's an okay approach.
Well, it is the exact same approach, right? If I pick any 2 points, I can estimate the line. If I pick any 3 points, I can estimate the line. If I pick any 4 points, you will be unsurprised to learn. If you pick 2 of the points and estimate the line, it'll be a lot less accurate than picking all 10.
Yeah.
And you might imagine that you could almost imagine probably that if you picked all possible 2-way grabs of the points, you might get much closer to the actual line as using all the data. But in a very intuitive sense, this is it, right? Any 2 points draw a line. Any 10 points draws a line too, and they're not going to be necessarily the same line. And the whole data is probably a better estimator than your favorite 2 points. Other questions? Okay, up next with problem 5 is Kiana. She made it.
Yes, I am. Just give me a second to pull it up. Okay, so let me share my screen. All right. So problem 5 was asking us to kind of solve for the values of VA and VD. They give us these correlations and the phenotypic variance. So I used the correlation for half siblings to find VA because we know that VD is 0 for half siblings, or not VD, I'm sorry, R2 is going to be 0 for half siblings. So I plugged in the values of R and R2 into that half sibling correlation. And I solved for this VA over VP fractions, the third. And from there I could solve for VA. And then I plugged that into the full sibling equation using the values of R and R2 for full siblings and the value of VA that we found previously. And from there, it was just algebra to find what VD is.
That's it. That's the answer. VA is 2, VD is 1, given those numbers. Perfect. Are there any questions about that? And that's the right order to do it in, because one of the equations had just VA in it, and the other had VA and VD in it. So just solve for one and then plug the answers into the other, rather than doing anything stupid and simultaneous. So clear to everybody? But this is also now the insight, right? Suppose you want to estimate multiple variance components. The right experiment is some sort of pedigreed experiment where you have multiple individuals with different sets of relationships, where, say, some of the individuals will just capture the additive component, other individuals will capture the dominant with the additive and the dominance. And if you were wanting to estimate interaction components, where, say, some of the individuals will share interaction components and others won't. And the more variance components you want to estimate, the more complicated your sort of pedigree is going to get. But in principle, if you think about it hard, you can sort of get the right design to get at just about any of the variance components you want, probably. You may need to postulate recombination between loci or something to get there. But this is the way you should be thinking about if you want to estimate variance components. If you just want the additive component, you can get at that by parent offspring. If you want anything more than the additive component, you're going to have to add in some other people like full SIBs. And from a single set of observations, you probably cannot get at more than one variance component unless you assume other things are 0. All sort of sensible. Christopher, do you want to try to take on the next problem? Did we make it there? Is Chris here? I think Chris is here. He was...
So I didn't quite get there.
Okay, you didn't make it? Okay. Brooke, did you make it to the next problem?
That's number 6.
Yeah.
Yeah, I think so.
Okay.
All right, 1 second. Okay. Okie dokie. So this was asking to find the heritability estimates for the given, oh my God, I can't even read my own handwriting. I'm sorry. For the different correlations or the regressions that were given to us. And so there were, I think, 7 different scenarios where we had the relationships. And so basically, I think it was just really applying the concept of heritability and what that was related to for the regression. So for an offspring on the father, I used the formula h²/2, setting that equal to the given regression to solve for 0.42. And then it's the same thing for the regression of the offspring on the mother, but we were given a different value. And then for full SIBs, I just put in the general equation, which was r(h²). And then I used really the first table that we had to to fill in for the various R1 and R2 values to come up with the answers. I think, and then when you are thinking about the mean of the parent, it's the regression is actually just H squared. So the heritability estimate is just what is given up for the mean of the parent. And then there's one other funky thing that needed to be done. And it was the regression of the daughters on dams. And I think this is because you're dealing with only, they have a really eloquent way of explaining it in the book, but you're basically dealing with only one set of, or one half of the population that could possibly be passing or having this regression. So you divide by 2 rather than from pulling from males. So
it's almost just like so within sires means you've like fixed a father. So you've now have the regression of mom on her daughters, and it just turned out all the different mothers hooked up with the same guy. That doesn't really change the regression of mom on daughters, and the correlation of mom with daughters doesn't really depend on whether all the different mothers have the same husband or all of them have different ones. The variance in that estimate surely has to do with whether or not we have one father or multiple fathers, but the expectation that isn't going to be dependent on them. So just like what you did right at the top.
all right.
And but these so you can now start thinking like the reason we have those words, and you can start thinking about now making complicated experiments where you start estimating individual, variance components when you say fix the fathers and allow the mothers to vary, or fix the mothers and allow the fathers to vary, or both, and we might be able to use that to get at some of these higher order variance terms. But the expectation is just the same as mother and daughter. Questions about this?
So I got a little confused in this question between when they were switching out regression or correlation. Are we
Yep.
effectively seeing them as the same? Or
Well, it was there just to ask, are you paying attention, right? So the correlation. So let's right. So here, let me share my screen. Let me be super. What am I doing? Share screen. So right now I'm showing you the mid-parent stuff, right? So in general, the regression coefficient is the covariance of one thing with the other divided by the variance of one thing. The correlation is the covariance of that one thing with another divided by the square root of the variance of one of them times the variance of the other. So when the two objects have the same variance, the correlation and the regression coefficient are necessarily the same. You can't separate them because the correlation is just the variance of one times the variance of the other square rooted. So if these are the same number, you're going to get one of those variances. If they are not, if they differ from one another, the regression coefficient is going to depend on who you're calling X and who you're calling Y. Because because we divide only by the variance of the thing you're plotting on the x-axis. And the correlation is no longer going to equal the regression coefficient because you have one of these numbers times the other square rooted. And that's definitely not going to be just one of those numbers if they differ. So the regression coefficient and the correlation are always the same if the X and Y values have the same variance. And they are always different if the X and Y values have different variances. So in these heritability type experiments, in these sort of pedigree type experiments, usually if the two things being compared are real individuals, they both have variance VP. They both have the population variance. If, on the other hand, you're looking at the regression of some constructed thing, like a mid-parent or the average of whatever, that might not have variance equal to the population variance. And the only way you're ever going to get this right is from first principles. You're probably never going to remember it or guess it, or well, you'll remember it eventually. But the only way I ever get it right after doing this for 20 years is to write down the correlation is defined as the covariance. Write down what I think the variance is. Oh, that's where the square root of 2 goes. I will not get that right without actually having to do it from first principles. I find it impossible. And if you are ever dealing with any kind of constructed variable against a real sort of person type thing, I would recommend writing it down from first principles, or there's a good chance you're going to be off by a half or a square root of a half or something stupid somewhere. Does that make sense? And remember this, the regression coefficient of mid-parent and offspring is almost a magic trick. It got a covariance that looked like VA over 2 with a population variance that looked like VP over 2. That regression was heritability is weird as hell. Most of the regressions are going to look something more like RVA over V2, because those covariances tend to look like, you know, RVA or RVA plus VD over VP. It's that the regression was heritability is almost luck. Well, it's defined that way because of this relationship. All right, let's stop sharing my screen, stop talking. Young Xian, what's the next problem?
All right, so the next problem is number 7, which is to get the expected rate of progress per generation. And for the 7-1, there we have heritability and then phenotypic variance and then proportions selected, and then the expected rate of progress per generation, which I understood as the R, which is equal to I times heritability times square root of phenotypic variance. So I looked up in the table in Falconer's book and then found that with 25% proportion selected from the parent population, the I will be 1.271. And then I calculated R from this formula and got 2.910. And then I also use same approach for different proportions and then different heritability and phenotypic variance and the proportion, for different traits.
So you've used a different heritability than I did. Did I misread heritability again? What's the heritability for the first? Was it 0.7?
I have
I have 0.37.
37.
Oops, sorry.
No worries. Okay. So I have the exact same calculation you do, only I'm using a heritability of 0.37 for the first several values, and I'm using the same 0.18 in 0.22. Okay, that's just a typo. So those are probably 3 sevens rather than 0.7s. Let's talk a second, guys, about this I over the square root of VP bit. So you all know, we know, we've probably learned, right, that the expected value of the offspring is equal to the regression coefficient of, say, parent on offspring times the value of the parent. And for many, many experiments, we're not going to measure the parents because we're cattle breeders and we're just going to put them on a scale. And if they're over something, we push them one way. And if they're under something, we push them another way. Or we're going to do that with our mice. If they're over some value, we're going to throw them one way. If they're under some value, we're going to throw them the other way. So we imagine the whole population is normally distributed with some variance of VP. And if we put a threshold on that population so that everyone above the threshold is allowed to breed and everyone below the threshold doesn't get to breed, we can tell you what the average value of the breeders are. The average value of the breeders is the integral of a normal distribution from the threshold to infinity times the value times the normal. It is the expected value of a normal from the threshold to infinity. It turns out that doing that integral is a little bit tricky. There's really only it's kind of numerical, very good, but really only numerical approximations to that integral. So instead of you having a calculator that can calculate what the mean is given a threshold, there are pictures and tables. And this problem asked you to look at a picture or a table to figure out what the mean was of individuals who were allowed to breed, given that you had a threshold that was set up so that, say, 25% of people could breed, or 50%, or 75%, or 10%, or 30%. And if you were good at calculus and a numerical approximation, you might be able to find that integral on your own. Otherwise, you might be best looking at a table or a picture to approximate what that is. And all the pictures and tables will be relative to a standard normal, a normal with mean 0 and variance 1. So if you don't have a standard normal, if you don't have mean 0, variance 1, you'll end up having to transform the value from the table or the picture to your scaled variance, which is here, sort of VP. So the response to selection is the regression coefficient. Because here we have two parents. It's the mid, because we have a mid parent here. It's H squared, the regression coefficient between mid parent and offspring, times the expected value of the parents given a threshold of whatever it was in the table, rescaled to this population's variance because my table was in a 0-1 normal. That's a lot of little things going on. It will take a few times probably for you to get this right consistently. But the reason you're using that funny little I guy is because, well, the reason you're given that funny little I guy is it's assumed you're going to struggle to do the integral of a normal. So this is a clever way to find the expected value of a truncated normal, or at least get to the answer of it without actually having to do any kind of numerical integration. And up to the difference between 0.37 and 0.7, those are, I think, the exact numerical values I got. Maybe the last one I got a slightly different numerical value, but I don't think it's very important. Does everyone think they understand how this problem was done? it's h squared because this is the regression coefficient of mid-parent on offspring. In general, it should simply be the regression coefficient of whoever you're comparing. The response looks like the difference between the selected people in their mean times the regression of who you're going to look at. We will see this a few different ways in a few different problems.
I have a question about the units.
Yeah.
So like when we're interpreting the values here in terms of the units they're in. So for instance, like the last one where you have litter size, you'd say like it would be like, oh well, the response is half of an individual or something. Which is that like correct way of saying that or no?
Yep. That's it exactly. Half a mouse. Say. 0.26.
I guess practically it might be kind of sorry. Practically it might be kind of difficult to tell if you know a mom is having on average 3 or like 2.75 litters, I guess. But anyway.
Well, your intuition is exactly correct, and you know exactly how to figure out your power, I'm sure, to tell those two apart. And you're not going to do it on 1 or 2 litters.
That's fair, yeah.
Right? This turns out to be actually a thing, right? That many mice geneticists, many experimental biologists in general are often trained in a sort of paradigm of looking for qualitative effects, where they're looking for, is it yellow or is it white? You know, like a clear, not clear, simple, yes, no kind of answer. And for many experiments, what they're actually doing is something akin to that, an experiment that might have resulted in 0.26 mice more per litter. And you will discover as you get older and into your career more that a shocking number of your colleagues who were trained in these model systems have no intuition as to whether or not 0.26 mice per litter is a lot or a little, and how many litters they should have done to have successfully estimated that difference. And if you interact with them a lot, you will find much of your time will be spent making sure they've done an experiment large enough to be able to successfully estimate the effect that they thought existed. If that makes sense. And I'm going to share my screen a little bit just to make sure we're on this problem, just to make sure we've gone all the way through it right. So I wrote down the full table where I have heritability, VP, the square root of VP, so this is sort of standard deviations, the fraction selected, and now therefore what I have estimated as the mid-parent value, which is in units of standard deviations above the mean. So when you select only the top 25%, I have the mid-parent being 1.27 units above the mean. When you select 50%, I have the mid-parent being that amount above the mean. When you select 75%, I have the mid-parent that above the mean. I actually probably didn't use the pictures. I may have tried to do the integration myself. When you're at the top 10%, you're about 1.7 units above the mean. When you're at 30%, somewhere in between those two, or a little less than that one rather, yeah. So the response to selection when Here, I'm selecting the first 4 of them. I'm selecting both parents. So this is really where the mid-parent is. The response is heritability times selection, scaled to the right standard deviation, and I got those values. Same thing for this tribolium, where these are mid-parents. So R is H squared S, scaled to that VP. This last one says I've selected only females. I haven't selected on male fertility. So the regression of mom on kid is, of course, RVA over VP. So that's R heritability. So that's a half heritability. So for this, when I've only selected girls, my response to selection will end up being half if I'd selected both boys and girls. The regression coefficient of mom on her kids is a half the regression coefficient of the mid-parent on the kids, as it turns out. And again, this is not really heritability so much as the regression coefficient, which was heritability for all of these mid-parents. The concept of heritability really came out of the abstraction of I'm doing this experiment, usually in mid-parents. It came out of the utility of defining everything in terms of heritability, because mostly I did the experiments in parent and offspring. I mean, in mid-parent and offspring. So up next is Taylor.
Okay. Okay, so bear with me, I didn't type out the problem. So it was 11.4 in Falconer and McKay. So we're basically given this data table for selection.
I'm sorry, I'm a 6-year-old boy. Your cumulatives are making me laugh. Sorry.
You know,
Sorry.
yeah, I just went with it. It's okay.
Yeah, I'm 6. We'll continue.
Yeah. So we're basically have a data table that has selection for increased and decreased plasma cholesterol levels in mice. So we have kind of 2 lines, high and low. And we're asked to calculate the realized heritability from the 2 lines separately and for the divergence. And we're, in the table, we're given basically generation 0 to 5. And then for both lines, M, which is the generation mean, and P, which is the mean of selected individuals to be used as the parents of the next generation. And so basically what I did was I typed up first for the high line, the values of M and P that were given, and then the response R is just the generation means that we were given. And then to calculate the selection differential, in generation 0, there was no selection acting on those, on them, so they weren't really their selection differential will be 0, and everything will be kind of shifted down 1 unit or 1 row. So the first value for the selection differential is 0, and everything else is just P minus M for the corresponding row above. And then I calculated the cumulative selection differential just by summing up the selection differentials we calculated. And then we can get the realized heritability by taking fitting a linear model of response on cumulative selection differential and taking the slope estimate. So for the high line, I got 0.63. And then for the low line, I got 0.362. And for the divergence, I calculated R, the response, by just taking the difference between the response in the high line and the low line. And same with the selection, again, calculated cumulative selection differential and did fit the regression again. And I got a realized heritability estimate of 0.512.
Something like that. Yeah, yes. Let me show you mine so it's slightly less mysterious in R what's going on. So have I successfully shown it? I don't think I have yet. Let's try. Can you guys see my screen? So This is just written out all the magic that Taylor decided to do in R, where in generation 0, I have the population mean. I have the mid-parental mean right next to that. So I can calculate the difference between the population mean and the mid-parental mean. That's that value S. That's just 0.32 minus that. Just that number minus that number minus that, and so forth. So my S's are just one number minus the other. And the response to selection is this generation's mean minus that generation's mean. So the first response to selection is 0.1. So if I'd only done this in one generation, I would have gotten a heritability of 0.1 divided by 0.16 or 0.625. If I'd only done the next generation, I would have gotten a realized heritability of 0. If I'd only done the next generation, I would have gotten a realized heritability of 0.63. So each generation, I get some realized heritability. And I might imagine my best estimate of the realized heritability is some fashion of averaging these. You could imagine doing a very naive average where I just add up all those realized heritabilities and divide by 5. I would have gotten about 0.45. Or perhaps a slightly better measure might be to look at the total sort of difference over the entire length of the experiment, which is 0.244 minus 0.216. The total response divided by the total sum of the selective differentials, which here the sum of that column turned out to be 0.45. And that suggests a total realized heritability of 0.62. Or I could have, there's probably a lot of other ways I could have averaged it. For the downward selection experiment, you get the exact same answer. It's the exact same procedure, and you end up with some realized heritability of a similar number of about 0.41. And you imagine if you take any kind of average between the two, you're going to get about a half. There are probably a lot of ways of doing that too. But does this all make sense to everybody? That in a single generation, I can estimate heritability. A better estimator is probably many generations in some sort of robustish way of doing it. But there are a lot of ways I could have made that estimate. Does this make sense? But the underlying data really is heritability every generation. So every generation, the population mean is moving because the parents are being selected. And in practice, that is what you do. So if you're doing these longitudinal experiments, you plot the response generation after generation against the selected coefficient, and you probably regress them to make a really robust estimator. Questions? Okay, up next is Julie with, I think we're on 9 maybe? 10? Where are we? 9.
Yeah, so I think we are first given the covariance between mid-parent and offspring, and we just calculated it was VA over 2. So VA is 50. And then heritability is VA over VP, and then the phenotypic variance is 100 kilograms, so it's 1/2. And since we want the mean to move up 5 kilograms, I just used this equation, and then to calculate the intensity of selection, which is about 1. And then if we look at the table, P is approximately 38%.
That's exactly right. That is exactly it. Does anyone have any questions about this? This is exactly how you do this problem. You first find VA. From that, you get heritability. And then We just need to figure out what the response to selection ought to be, which is again the expected, got to be able to integrate that normal, which is why you're going to end up with an I in there and a square root of VP. So if we select 38% of the herd, we'll make it all go down the road. Any questions? This is literally what cattle breeders do, honest to God. Like, people were doing this, in Iowa, like in the 1920s, 1930s. And question.
I was just going to ask, so maybe this is answered in later questions I haven't gotten to quite yet, but why not just increase the selection differential anyways? I mean, I guess this is assuming you only want it to go up to this 405. And if you did that, you might get a higher average.
So
is that the idea?
So nothing about this homework is going to answer your question about that. So when we read the Torelli and Barton paper, they will talk about that some. And what they're going to talk about is this field. The term of art becomes something along the lines of the limits to selection. And it turns out that the faster you, like the more extreme you truncate the distribution, you end up selecting for alleles of larger and larger effect, which also tend to be alleles with larger and larger pleiotropic effects. So it will turn out that the way biology is there are alleles to make you a better, fatter, better tasting cow. And we might even be able to select forever on making better tasting cows, except for the fact that those same alleles have other effects. And say for better tasting cows, those other effects might be cardiovascular disease. Because while we're selecting for them to be fatter and have fat all throughout their body so they taste yummy, that effect is to give them heart disease younger and them to die, say, before they ever get to be a fat, tasty cow. So we will discover from years of these breeding experiments that I can push that mean around in 1 or 2 generations almost as fast and far as I want. But the cost of doing so tends to be I pull along all these alleles with horrible pleiotropic effects. And while I might have hit the mean I wanted, I got all the cattle are so sick that very few of them actually make it to that size, or hardly any do. And I find that when I select fast, I tend to very rapidly plateau and can select no more and often get sicker and sicker and sicker individuals. On the other hand, people discovered in the early 20th century, when I select very slowly, it's not obvious I can't select forever. And there are these experiments in Iowa where we're selecting for, say, corn that has a higher sort of oil content. Those experiments have been going on 120 years and have not shown any evidence of hitting a limit. That if you select corn slowly, you can keep going up. Although that's not quite true. The experiment that is trying for more oil may be going up more or less forever. The experiment that was trying to make less oil has probably plateaued, in part because there's probably a minimum amount of oil you can have in a corn to have it still be corn before it's no longer viable or you've hit the amount 0. So what we often discover is we can select for bigger for a lot longer than we can select for littler. That littler will reach a limit of selection and plateau faster than the experiment that goes bigger. And the rate at which we approach that plateau and where that plateau is is often a function of how gently we do the selection. And there's nothing about your homework that will teach you that, but hopefully the Barton and Torelli summary won't be so fast and hard. You won't be able to glean that from. There's a lot of, reading that paper is like reading from a fire hose. In every paragraph is saying something different. And so there's a lot of material there, including this, that the limits of selection tend to be very different on your up versus down. And when you select slow enough, there's no obvious limit in many experiments on the upside.
Is this related to the term? Oh,
Yep.
sorry, my connection's unstable. So is this related to the term clonal interference? Because I've heard that term thrown around a lot. I didn't necessarily understand it.
So clonal interference is usually used in a slightly different context. It's usually used to mean the not pleiotropic effects of a single mutation, but the linked effects of multiple sites. So if you were in a system where there's very little recombination and you select for one allele, that allele may be in LD with other alleles, and the thing they're in LD with may have the opposite effect, say, of what you're selecting for. So that you can't you can't select for what you want because it's in linkage with the thing sending you the other way. And they are interfering with each other's ability to evolve because they lack recombination between them. That's usually what people are talking about when they're clonal interference. It really is not the pleiotropic effects of one allele, but the combined effects of multiple alleles that are difficult to separate from one another. Other questions?
Can I ask another question? So if there's like a limit to the lower bound, does that kind of violate the normality assumption of phenotypes?
Yeah, so I'm not going to do it. We're not going to do it. But it also turns out that when you do these selection experiments, the variance actually changes from one generation to another. So again, when we read Barton and Torelli, they will probably present that formula. They will probably call it, who the hell derived it first? What's his name? I forgot. Anyway, we'll get there. It turns out in these selection experiments, the variance changes from one generation to another. And when you go down, you're approaching a situation where there's closer to zero variance faster. And literally, in a very formal sense, the reason we plateau is either because there's zero variance or because there's these pleiotropic interactions that stop us. And you can tease those two apart in an experiment by sort of like estimating how variance is changing in it and deciding whether or not you're plateauing because you've run out of variance or you're plateauing because you've gotten pleiotropic interference. The loss, it turns out generally you probably still have variance usually, but not always. And if your experiment is long enough, we can also sort of think about this, that there is standing variation in the population. If you select for several generations, you may soon exhaust all the standing variation in the population. But every generation, mutation will be introducing new variants. So, so in these experiments that are done in Iowa, where we're doing year after year after year after year, what we're actually probably doing is reaching some sort of stable equilibrium where the amount of variation we are losing because of the selection experiment is less than or equal to the amount of new variation coming in due to mutation. And almost surely the original population variation was gone long ago. And these are now effectively mutation accumulation experiments. These are experiments that we're measuring variance that was newly acquired during the course of the experiment. If that makes sense. Other questions?
Can you go over the difference between clonal interference and a Hill-Robertson effect?
As far as I'm concerned, they're the same thing, whether or not, but Hill-Robertson is usually on a positive versus negative S. So these terms are not used perfectly. They are not used, even people in the field often do not know exactly what they mean when they're saying these things. But in general, so Hill-Robertson effect is the change in the rate of selection at one locus due to linked selection at another locus. And that is very much what I just described in clonal interference. Most of the time when people say Hill-Robertson, they are imagining S is positive at both loci. And there's even a slowdown even when S is positive at both loci. They often use clonal interference when S is positive at one and negative at the other. So that they're like going in opposite directions, but not always. You'd have to almost ask people what they're meaning by it. Hill-Robertson derived the sort of mathematical framework to allow you to estimate this. And if you're interested in rates of evolution in these linked systems, Hill-Robertson is a good place to start with your sort of estimation framework, if that makes sense. Recombination is powerful, though. Recombination is real powerful. And unless you're in a system that is like E. coli or something where recombination is very rare, there is often little utility to these multi-locus sort of problems that effectively most loci are independent of each other for most organisms that have recombination. Questions? Up next. You're up next, man, with the next problem, whatever that is.
Okay, I think my next problem is not perfect, is not correct based on what I saw from Julie's page, but
let's see.
But here it is. So this time we have actually this is not the page. Oh wait, no, this is the page. So this time we have chickens and they produce 20 eggs on average each month with a variance of 16 eggs. And on average, how many eggs per month the next generation of chickens will produce if we only select the top 20% for breeding. And suppose we know the covariance between full SIBs is 7 and the variance due to the dominance effect is 4. So I didn't see why we had this dominance effects given but until I saw the previous presenter's solution. But so I think this is not correct, so to speak.
Yeah. Okay. Let me show you mine. But yes, we're getting there. So let's see. Why am I doing this? Share screen. This one. Yep. So we start with the covariance of full SIBs, which is RVA plus, you guys can see my PDF, which is RVA plus R2VD. The problem said the covariance is 7. So VA over 2 plus VD over 4 is 7. The problem told us that VD was 4. So 6 equals VA over 2. So VA is 12. The problem suggested that that VP was 16. So what we have is heritability is VA over VP, which is 3/5. If only the top 20% breed, that corresponds to 1.4 standard deviations above the mean. So S is 1.4 standard deviations. So that's 1.4 standard deviations is also 5.6 eggs. So my response, these are mid-parents, right? So my response looks like heritability times 5.6 or 3.3 eggs. Is everybody happy with this? And that was, I think, effectively what you showed, except we didn't quite get VA exactly right.
I had a question about this one. So when I read this problem, I kind of thought it was similar to problem number 7C, where the trait that you're looking at is litter size. And so it's only selected in females. I assumed here that you're looking for.
You know what? You might be right.
So I divided I by 2.
You might be right. I think it probably is too. I think I got my own problem wrong. I think you're probably only able to select on females. In which case, this really should have a factor of a half in it. I think you're probably right. That that I have only selected, say, females. I think I have some weird assumption in here that that female chickens can breed with themselves. And if there are any roosters involved, there ought to be a half. You are totally right. I am wrong. That the regression coefficient is a half H squared unless female chickens can breed with each other. Assuming there is a rooster, it should be a half in here. You're right, I'm wrong. Thank you.
So can I also ask about the final value of R? Because I was kind of thinking about it as how that's a deviation, or not a deviation, but that's.
Yeah, it's a deviation from the mean.
Right. So if the mean in the previous generation was 20, would you not, like, would the new average of eggs in the new generation then be 20 plus the value that we just solved for? Okay.
23.36 is the new mean. Or if you're correct in your Taylor, it's actually it's 21.7, say.
Okay. Cool. That makes sense. Thank you.
The response is 3.36 eggs. The new mean is 20.36 or half that, 21.7-ish, whatever. Yeah, in my own problem, I sort of forgot about the fact that chickens are just female. Thank you. Has everybody gone today? Who's here? Have I missed anybody? Is Mitchell with us? I don't think he's with us. If everybody has gone today, I think now is a good time to stop.
I have not gone.
You've not gone? Ah, yes.
No.
Do you want to give us number 11 or can you?
Yeah, I don't know if I did it right.
Go for it. Yeah, there you are, Mitchell. I lost you there.
Oh, 11? I definitely think I did it right.
Good.
So maybe not actually. It's a long description of stuff. asking about, you know, like trying to think of maybe quantitative traits as these threshold values. So it gives a liability for autism to have a mean of 0 and a variance of 1. And then a probability of having autism of 1 in 68. So I was asking, what would the threshold be? So basically the problem set up a normal distribution with a mean of 0 and a variance of 1. So that's just the standard one. So I just took the threshold value of, so I just found the probability that you gave was 0.0147 and found the threshold value that corresponded to that probability using a standard normal table, and I got a threshold of 2.17.
Exactly perfect. Yes. So this is where we're going to stop for today. And we'll do all the qualitative kind of human genetics problems next time. But this is the setup. We're going to think of every single qualitative trait as if there is a normal distribution that gives rise to that trait. And we're just observing it wrong. We're not observing the underlying normal distribution. We're just observing a threshold on the normal. So that people who are above the threshold, we see as being one phenotype, and people below the threshold we see as being the other phenotype, without being able to observe the underlying quantitative trait. This is how we're going to model everything on Earth. And when we model everything on Earth in this fashion, the people who are above the trait, we can often think about like they were a selected group. And we can often think about what would have happened if this had been a cattle breeding experiment and these had been parents, and I ask, what would the mean of the offspring be if I had truncated things like this? Or if, say, I had looked only at the offspring of people who happened to have exceeded that threshold by chance. So if, say, I'm going to start looking at these problems like, suppose dad has a disease, what can I predict about his offspring? I know how to do that for these breeding experiments. It's going to be the same answer. The expected value of the offspring is going to look like the expected value of the parent, the mean of the parent, times the regression coefficient between them. And so for these human genetic experiments, I'll ask, what is the regression coefficient between the two people I'm looking at? What is the mean of the parent, or the mean of the, say, diseased population? And what is the mean of the relative? And I will be able to predict how often a relative ought to have disease as a function of how often the first guy has disease, using these classical animal breeding equations. And using these classical animal breeding equations, and sometimes in some of these little straightforward applications of Bayes' theorem, I'll be able to even tell you what allele frequencies ought to be in one group versus another group, using all of this machinery. And these next several problems are going to be how you go from, say, observed allele frequencies in cases and controls, to fraction of the variance explained, to predicting relative risk. as a function of this locus. And it is through this quantitative genetic framework that we will be able to link together the quantities that we usually observe in a genetic experiment, an allele frequency, to an estimated effect size on the liability scale, to the amount of variance this locus is explaining, to even decompositions of the variance at the locus, and so forth. And the last 13, whatever, the last 5, 6, 7 problems you've done are literally nothing more than what you've already done, disguised. Maybe with a few little Bayes theorem stuff thrown in. And we will go over all of them in some detail next time so that we have some sort of practice relating allele frequencies to effect sizes and so forth. And sort of very useful stuff for the few human geneticists here. Do we have any questions?
Can I ask a clarifying question about like 11?
Yeah.
So when I'm visualizing this like normal distribution for the liability, should I be thinking that the autistic individuals would be the ones that are more than X away on one side, or would that be on both sides of the distribution?
I would think of it as one side always. I would always think of it as one-sided.
Okay. Gotcha.
It's a good idea, but it's also probably right. It is probable that if there is, say, a true liability scale, the idea is, you got a threshold above that, you'd say they're autistic. But in reality, that threshold is probably arbitrary. And people on the other side of the threshold will probably seem pretty damn autistic, measured in many ways, just not quite autistic enough for you to call them autistic. That by some measures they are and some they aren't. And people like right on the other side of that threshold are probably like barely autistic. But those, say, 3 standard deviations out are those that everyone on Earth would recognize as autistic. The other end of that distribution is probably people who seem nothing like autistic, who seem that they are, sort of incredibly communicative and incredibly emotive and very sensitive to everyone else's thoughts and feelings. That at one end are those that struggle with communication and emotional interpretation, and at the other are people who are probably exceptionally good at it. And certainly it's even easier to think about this when if we had called the trait to start with basketball player, and this had been height, that we may have not been able to observe underlying height, but we could observe basketball player. But the other end of basketball player are really short, and quite obviously really short. And we imagine that's probably going on for everything that we're talking about. So, if this were, say, some measure of intelligence, on one end are probably people we would identify as very bright, and then at the other end are those that would identify as very not so bright, and so forth. It's, for many of these traits, it's quite not obvious it's even hard to imagine what is the opposite of schizophrenic. At one end, okay, we got schizophrenia. I don't know what not schizophrenia, what especially unschizophrenic is, but never ever hearing a voice. I don't know what that, but it's probably not, it's whatever it is, it's extremely unlikely to be mistaken for schizophrenia by, say, a clinician. That's sort of the way I would think about it, whatever it is, about that other end.
Yeah, so I was totally thinking about it wrong. I was thinking like there was an ideal, I guess, threshold around mu equals 0 where everything was working right, and then when you're out of that, it's not working right. But
Yeah,
okay,
well,
I see.
that's probably actually true. It's just you're probably broke it in different ways. So for whatever the opposite of schizophrenic is, it's probably not totally great, but just not in a schizophrenic way. And whatever the opposite of completely of autistic may be so emotionally liable you don't function well. It's probably not good for you. Otherwise, we imagine that truncation selection would probably be moving the distribution in away from say autism ever existing. It's actually hard to breed with autism. So if we would imagine the population were going the other way if there weren't probably selection at the other end against it for something.
Can I ask one more clarifying question for 11?
Yes.
This is more equation related. Because I know one way that you can approach trying to at least get a z-score would be to use a subtraction of x, or subtracting the mean from x over the standard deviation. That's
Yes.
like, but I think when I was doing it, I realized like, okay, well, let me put in 1/68 into x, and then I didn't think that 0.014 was the z-score. But when you subtract it from, I think, the value of 1, you can get the area under the curve that is corresponding with the z-score. But I don't really know how I ultimately like kind of made that intuitive leap. And so I wonder if there's like a better way to explain what x is.
So the only way I can ever do this is you've got a table in front of you.
Mm-hmm.
Table, you have to look at really carefully what it's giving you. Is it giving you the area from -infinity to some value x? Is it giving you the area from 0 to x? Is it giving you the value from x to infinity? Honest to God, the tables could be doing any of those things. So it might be giving you -infinity to x, but chopping off x at a negative number. It could be giving you from 0 to a positive number and ignoring this half of the distribution. It could be giving you 0 to whatever it is, and it could be giving you this to beyond. I don't know what the standard ways of those tables are. I haven't looked at them in many years. And I can't ever interpret them unless they have at the top a little integral that shows me I'm going from -infinity to x. Am I going from x to y? Am I going from y to beyond? Am I going from a half, from 0 to x on the positive end? And your intuition is if something like looks weird or backwards or off by a half, it's because the table you're looking at is not doing what you wanted. You wanted from -infinity to x, and it gave you from 0 to x. Or you wanted beyond x, and it gave you from 0 to x. You can get there by adding a half, subtracting 1, going upside down or right side up. You will be able to get home. Always, whatever they gave you is probably sufficient for what you needed, but you might have to just go 1 minus that, a half plus that, 1 minus, and so forth, depending on how you constructed the problem and what the table gave you. Does that make sense?
I think so, because so basically like the area under a curve.
Yep.
In this sense, when we're looking at a normal curve, is basically going to be like the total area should be 1.
The total area is always 1.
Okay. Yeah.
And the total area from 0 to infinity or from -infinity to 0 is a half.
Okay.
So they have assumed that you know 1.5. It's going to be off by 1, a half, 1 minus that, or a half minus that, probably, depending on which way around this thing's being reported. Other questions? Okay, the last several problems are challenging, and they are relating everything we've learned so far to each other. And if you struggled with them, do not feel bad. We will go through them all in detail. But the goal is for, by the time the homework is over, for you to be able to do this sort of thing. And while not getting them right the first time is exactly normal for everyone, by the end of Thursday, you'll want to be able to do them. So, so pay attention. We'll go over my solutions to them. We'll go over your solutions to them, and hopefully by the end it will all make sense. See you all Thursday.